Okay, so area of a regular polygon is 1/2 AP. We have to understand what A and P stand for. P is something you already know, perimeter, right? Perimeter is just the distance around the outside, right? So the length of adding up all the sides. A stands for apothem. Apothem's probably a new word for you. The apothem is the segment that you draw from the center of a polygon straight down perpendicular to one of the sides. That's the apothem. Now, you will probably be given this formula on the final exam, especially you will be given this formula. But important to understand that it takes a lot of practice in using the formula to really be good at it. They are not always going to say, okay, here's the formula, 1/2 AP, and A equals this, and P equals that. Now just plug it in. That's not the way these problems are going to go. You're going to have to figure out what A is, and you're going to have to figure out what P is. Okay, so it's going to be a little bit more involved than it looks right away. Okay, so let's look at this hexagon for a second. This is the apothem drawn straight down. It basically goes from the center to the edge, the side of the polygon. And since it's a regular polygon, when we do that, it splits that side in half. Okay, that's the apothem. I'm going to label it A. Now you'll see in the diagram on the first page also, they have drawn a segment that goes from the center to the vertex. Center to the vertex, that's called a radius of the polygon. Now we're used to the radius of a circle, right? A radius of a circle can be drawn in any direction and it's always the same length. But if we go in any direction from the center, is it always going to be the same length? No. So in a polygon, this is a hexagon, there's only going to be 6 radii in a hexagon. And they all go from the center to a vertex. Okay, that's a radius. So the apothem is shorter than that. It goes from the center perpendicular to the side. Anything in between is not really useful. Okay, let's go back to this. A couple of words that are important here. A regular polygon, again, all the sides are congruent. All the angles are congruent. This formula only works with regular polygons. Radius we just talked about, vertex to the center. Apothem we just talked about. The central angle we're going to talk about a little bit more later. But if you remember the central angle of a circle, if you have 2 radii, they form the central angle of a circle. Well, the same is going to be true with a polygon. If you take 2 radii, that angle that the 2 radii form is called a central angle. Vertex is at the center, right? It's called a central angle because the vertex is at the center. So central angles we're going to talk about in a little bit. All right, so we'll do this nice first easy one to ease ourselves into it here. Formula is 1/2 AP. We need to know A, we need to know P. What they've given us is this labeled diagram here. What's the A? 12.3. What's P? Well, each side is 8. We'd have to know how many sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. So what's the perimeter? 80. So we're all set to plug into our formula then. Nice and easy. They gave us the apothem. It was easy to calculate the perimeter. 1/2 12.3 times 80 is 492. Since this is inches and we're talking about area, we need square inches. Okay, so Sometimes they're not going to give us the apothem. They're going to make us work for it. What I want you to remember in this whole process is that this triangle here is the key to finding the area of the polygon. Okay. In order to figure out the apothem and the perimeter, this yellow triangle that I highlighted here is what is going to become an important triangle, where if we know the length of this side, that'll help us get the perimeter, right? Because if we know that little piece, we can figure out the rest. If we can figure out the length of this side of the triangle, that gives us the apothem. So between those two sides of this little triangle, we can get the 1/2 AP. Now, we know it's a right triangle because the apothem is perpendicular. What's going to become important is this angle right here. Okay, that angle is going to be the key to figuring out the sides. They do have to give us one piece of a length, you know, either a radius or a length of a side or something. They have to give us something. But we also are going to use this angle that I marked here. We can use that because we can always calculate what that is. This is where we're going to use that idea of a central angle. The central angle is this whole angle right here. Right? Two radii form a central angle. Well, if this is a pentagon, we see that there's 5 sides. How can we figure out that central angle measure? Yeah. Good. 360 divided by the number of sides, or the number of central angles, right, is going to give us the degree measure of each angle. So they have that actually labeled angle 1. You see this angle 1 right here? That's a central angle. So we did 360 divided by 5, and angle 1 is going to be 72 degrees. Angle 2, they have measured angle 2 right in here, but that's the angle that I highlighted for us here, right here. This is angle 2. That's really the angle we worried about. That's the one, that's our goal, to get that angle. We start with the central angle because it's easy to get, 360 divided by the number of sides. But to get that angle that we really care about, we just have to cut that central angle in half. So the measure of angle 2 is just half of angle 1. So 72 divided by 2, or 36 degrees. Now, in all of these regular polygon problems, I'm going to ask you to take that key triangle, that yellow triangle, and kind of pull it out and redraw it and label it. We have this is 36 degrees now. The next thing they're asking us for is the measure of angle 3, which is up here, but in this triangle, it's this one. How can we get angle 3? They add up to 180, right? So we've got 90 plus 36 plus this measure of angle 3 equals 180. And so measure of angle 3 in this case is 54 degrees. Now, I'm going to kind of put parentheses around that one because honestly, in the big picture, we don't really care about that angle. And the only reason we care about the central angle is because we need half of it. So I guess what I'm saying is this is the angle that we really care about. That is really the one and only important angle. Okay, so they're giving us a hexagon down here, and they want us to find those same angle measures. sometimes this book has some inconsistencies in it, which is why we don't use the book a lot. Sometimes it's frustrating, but you see how they have angle 1 is the central angle, again, here. But then they mix up the 2 and the 3, different than the one we just did. So I would like you to change this little 3 to a 2, and this little 2 to a 3. Because I want it to match the one we just did. Okay, so find the measure of each numbered angle. Measure of angle 1 is a central angle. So how do we find the measure of that? How many degrees is it all the way around? 360. Cut into 6 equal central angles. So what's the central angle going to be? Oops, I did 60 degrees each. Good. Measure of angle 2, remember? The significance of angle 2 is just to cut angle 1 in half. So measure of angle 2 in this case is 30 degrees. Measure of angle 3, again, we don't really worry too much about it. But if we redraw this triangle, we have a 90-degree angle there, we have a 30-degree angle here. What's this other angle going to be? 60 degrees. And isn't that a nice special triangle? Yeah. 30, 60, 90 triangle. Remember those? Okay, so special right triangles are going to be important in this section, especially 30, 60, 90s. So just don't forget, 45, 45, 90, sides across from the 45s are both S, and the hypotenuse is S root 2. With 30, 60, 90, the side across from 30 is always S. The hypotenuse is twice that, and the side across from 60 is S root 3. By the way, I just wanted to mention about this formula. It may seem random, but if I asked you to find the area of this triangle, and I said the length of the side is x, what would be the area of that triangle? How do you find the area of a triangle? 1/2 base times height, right? Okay, so this yellow triangle would be 1/2 base is x times height is a, right? I'm going to do the a first. So if I got the area of this triangle, but then I wanted the area of the entire regular polygon, what would you do? Multiply it by the number of triangles there are. In this case, 6. So you would multiply this by 6, right? Well, what would 6x be representing in this polygon? The perimeter, right? If this is x, and there's 6 of them, 6x would be the perimeter. So you see where that 1/2 AP comes from? It's basically the area of the triangle times the number of triangles. Make sense? Okay, so let's go back to this. We just discovered that in a hexagon, this important triangle that I said always highlight that important triangle, in a hexagon, it's a 30, 60, 90 triangle. Well, that's always going to be true for every hexagon. It's always going to be a special right triangle, 30, 60, 90. Now, that's not true in pentagons, octagons, any other gons, just in hexagons. So when it's a hexagon, that's what you should think of. Aha, 30, 60, 90 triangle. All right, so I'm going to take this triangle, and I'm going to redraw it here. Now, be careful with this one, because before I drew this, what is 12 meters the length of? the radius, right? So it's right here. Maybe I'll draw my triangle like this so we don't get it confused. Okay, so 12 is the radius. I'll put it here so that it's facing the right way. This is the A. This is our apothem right there. Now, since it's a hexagon, what kind of a triangle is this? 30, 60, 90. Where this one's 30 and this one's 60. So the side across from 30 is S. Hypotenuse is 2S. Side across from 60 is S root 3. Well, remember, go to the side that they have labeled with a number. 2S equals 12. What's S? 6. So what's this side? 6. What's the apothem? 6 root 3. Okay, so in our hexagon, this piece here is 6. What does that make the whole length of the side of the hexagon? Each side. Yeah, perimeter would be 72, right. Okay, so this shape is a hexagon. The length of one side is 12. The apothem is 6 root 3. Perimeter then, 6 sides, each one is 12. 6 times 12 is 72. Well, as long as we have that, we can get the area. 1/2 AP. Apothem is 6 root 3. Perimeter is 72. Area equals 1/2 AP. Notice they've given us 2 blanks here. The first blank is for the exact form. The second one is for the rounded or the approximate. So, exact form, we're going to leave the root 3 in there. And we just need to multiply the numbers together. 1/2 times 6 times 72. What's 1/2 times 6 times 72? 216, I think, right? 216 root 3. This was meters, so square meters. Now just plug 216 root 3 into your calculator, and you'll get your approximate 374.12. Again, square meters. Okay, number 2 is also a hexagon. So again, that right triangle that you pull out is going to be a 30, 60, 90 triangle. In this case, however, they don't give us a radius, they give us the length of a side. So I would like you to try number 2. So again, we have a hexagon. So you would take this triangle like this. This is your apothem. Here's your right angle. If this whole side is 10, when you draw this special right triangle, got 30 here and 60 here, what's the length of this side? 5. So in your triangle, S is 5. Side across from 30 is 5. Apothem would be what? 5 root 3. Now, they already told us the length of the side of the hexagon is 10, which makes the perimeter 60. So now we're ready for the area. 1/2. Apothem is 5 root 3. Perimeter is 60. You should have gotten 150 root 3 for the exact. And the approximate was 3 something. Nope, 259.81. And this was centimeters, so square centimeters. Okay, number 3, I'm going to let you do on your own, but they are pointing to the apothem is 4 root 3. Again, it's a hexagon, same relationship, 30, 60, 90 triangle. Let's look at number 4. It says there's 2 different ways of finding the area. I would say there's probably more than 2 different ways. Yep. Yep. Okay, so here they've given us this length is 2. What would you call that? Is that an apothem or a radius or a side? What's that? It's a radius, right? So each one of the radii are going to be 2. So when we create the right triangle in here, now we have our hypotenuse is 2. Well, what kind of a triangle is this? Is this a special right triangle? Well, if this is an equilateral triangle, what's this whole angle? 60. And if it's 360 around, what's a central angle? 120, right? Okay, so therefore, yes, this is actually a special right triangle. If this whole angle is 60, we cut it in half, it's 30 down here. If a whole central angle is 120, we cut it in half, it's 60 up here. So it actually is a special right triangle, it's just turned in the other direction. Our apothem is not the s root 3 now. What's our apothem? Just s. Remember, the hypotenuse is 2s. This is just s. And down here is s root 3. So it's a little different, right? It is a special right triangle, but it's facing a different direction. Okay, so if we're going to use 1/2 AP, what's the apothem? Right here, what's this? 1, exactly, because it's half of 2. What's the perimeter? Well, that's a little bit different. Right here is 1 root 3. So what's the length of a whole side? 2 root 3. Well, if each side is 2 root 3, what's the perimeter? 6 root 3, because there's 3 sides. 3 times 2 root 3 is 6 root 3. So we have 1/2 times 1 times 6 root 3, which is 3 root 3. Of course, the other way that you know, that's kind of the first way. We could do 1/2 base times height. Of the whole triangle, 1/2 base. What's the base? 2 root 3. Right? That's the length of this whole side is the base. What's the height? Well, it's 2 from here to here. Can't see what I'm doing anymore. 2 from here to here. And then we said the apothem is 1. So what's the whole height? 3. So 1/2 base times height is 1/2 times 2 root 3 times 3, which is still 3 root 3. So it doesn't matter how you do it. Remember that 1/2 AP works if something is a regular polygon. So, you know, it's an option as long as you have all the sides of are congruent and all the angles congruent. Hexagons had special right triangle in them. The equilateral triangle had a special right triangle in them. Both were 30, 60, 90. One was turned one way, one was turned the other way. What shape would get you a 45, 45, 90 triangle? A square, right? But typically, could you use 1/2 AP to find the area of a square? Yes. Typically, that's not usually the way we find the area of a square, but you could. Okay, this is important. We got to do this one. We're running low on time, but we got to do it. Okay? We have here a nonagon. 2 hints. Hint number 1, there is no special right triangle in a nonagon. Hexagons are the only ones Equilateral triangle, yeah. Less common that we would use this formula with that, though. So, if it's not a hexagon, you're not going to have a special right triangle. We have a nonagon here. We are going to do the same process of pulling out this right triangle. Even though it's not special, it's still the triangle that we have to focus on. Again, like I said before, what we care about are the length of this side and the length of the apothem, which is the height of this triangle. In order to make this work, the angle that we care about is that little angle right there. Now, we have a nonagon. Each side is 10. If there's 9 sides and each side is 10, what's the perimeter going to be? 90. All right, well, we have 1/2 AP, and right now we've got the P. That's good. We just need the A. In order to get that A, we are going to have to use this triangle that we pulled out. Again, start by finding the central angle. If there are 9 central angles, how are we going to get the measure of one of them? Yep, 360 divided by 9 gets you the measure of one central angle is 40 degrees. That is what we have right here. Remember, the central angle, though, is not really the one we care about. We care about this little one here. What's going to be the measure of this one? Half of the central angle, so 20 degrees. Now, if each side is 10 on this nonagon, what's this? 5. Right? That's going to be 5. This is not a special right triangle. How are we going to get the apothem? SOHCAHTOA. What are we going to use? Sine, cosine, or tangent? So here's the reference angle, 20 degrees. Side PS is O or A? O. Apothem is A. Isn't that nice? A for apothem, A for adjacent. It's the same thing. Okay. Hypotenuse is over here. In this particular problem, we don't know it and we don't care about it. So what are we going to use? Sine, cosine, or tangent? Tangent, right. Tangent of 20 degrees equals opposite 5 over adjacent A. Remember, we're going to put this over 1. We're going to cross multiply. We're going to solve. A times tan 20 equals 5. We have to end up dividing by tan 20 on both sides. So on your calculator, you're doing the apothem equals 5 divided by tan 20. What does that come out to? 13.74. So that's the apothem. So area is 1/2 apothem times perimeter, which we said was what, 90? So we're going to do that on our calculator. We get 618.18 if you kept it exact as long as possible. You might have had 618.3 if you rounded. And this was meters, inches, what was it? Centimeters? Square centimeters. Okay, we didn't have a chance to do this one. Each side is 4. Remember, you have to pull out this triangle. Central angle, and then cut it in half to get this degree measure right here. Okay? 5 sides. All right.